Start with a new schematic. Now we're going to again look at some series and resistors, some resistors in series and parallel with a DC voltage source. So let's start with a DC voltage source. We're going to add a few resistors here. So that's our circuit. Now let's connect the wires. And we're going to finish this off with a ground. Okay, now we have our circuit. Let's just name the values for the components. So I'm going to say this is 5 volts, so it's our DC source. The resistances are all going to be 100 ohms. Okay, so that's our circuit that we're trying to analyze. And let's see what we're dealing with. So the first question I have for you is, do you think resistances R1 and R2 are in series? No, they're not. They're not sharing the same current. There's a split in current over here. The current goes here and some goes here. So they're not sharing the same current. They're not in series. So what are they then? Well, we can see that do you see a relationship between, or some sort of series parallel combination between R2 and R3? Yeah, R2 and R3 are sharing the same nodes. That means they're sharing the same voltage across them. That means they're in parallel. So R2 is in parallel with R3, which means that we can combine them. And how do we combine them? Always, let's see. So what's the parallel combination formula? 1 over R, so the resultant R equals 1 over R2 plus 1 over R3. So 1 over R equals 1 divided by 100 plus 1 divided by 100. And so R would be 50 ohms. And how do I know that without calculating it? Well, here's a shortcut for you. Anytime there's a parallel combination of resistances and the values are the same, so 100 is in parallel with 100, then the resultant resistance is just going to be half of both of them. So over here, half of 100 is 50. So our resultant R equals 50 ohms. So for that, basically what I'm going to do is I'm going to reduce this one to 50 ohms. And I'm going to remove this guy, R2. We don't need that anymore. So this is our resultant circuit. Now do you see a combination over here between R1 and R3? Yeah, they have the same current flowing through them, so they are in series. So let's try to calculate the current that's flowing through R1 and R3. So to calculate the current going through both of these resistances, say the current I. So we're trying to calculate I. So from Ohm's law, we know that V1 equals I times R, which is basically in our case R1 plus R3. So this makes it so V1 or I equals V1 divided by R1 plus R3, which is 5 divided by 150. What is that? So 5 divided by 150 is 0.33. Let's multiply by 1,000 is at 33.33 milliamps. That's the current flowing through our circuit. Now, before we simulate, there's one more thing I want to see, which is what is the voltage at this node, which is between these two resistances R1 and R3. There's a few ways you can calculate that. The first one, we already have the current. So the current times the resistance R3 should give us the voltage at this node. So let's say V node equals I times R3, which is equal to 33.33 milliamps times R3, which I'm going to just say is 50 ohms, yeah. So let's bring out our calculator again. So 33.33 milliamps times 50 is 166. And this is going to be in millivolts, so let's divide by 1,000. So basically I have 1.66 volts is our voltage at the node. What's the other way of calculating this? It's called voltage divider. So we're not going to get into the theory of voltage divider, we're just going to see how we're going to apply it here. If you want to learn more about this, if you don't know already, you should look it up before you continue down this road in this lecture. But let's get to it. So voltage divider would be another way of calculating the voltage between these two resistances, a very commonly used formula. And so that would be V at node equals V1 times the resistance, basically the resistance to ground from the node that we're trying to calculate, so which is R3 divided by R3 plus R1, the total resistance from the voltage source of V1 to ground. So this should give us the same answer as before. Let's see, 5 times 50 divided by 150. 5 times 50 divided by 150. What is it? What is it? So 5 times 50 divided by 150, that is again 1.66 volts like we expected. Great, so we have our voltage at that node. Okay, so one more thing before we simulate, that's how do you know, just intuitively, if this voltage that you calculated is correct or not? It's very important to get that intuitive feeling when you're dealing with circuits. So how do I know that this is correct? Well, I know that we have 5 volts at this source, and then we have ground here, right? So we have 5 volts at this node and ground here. So that means the 5 volts is getting dropped across R1, and then some voltage of the 5 is getting dropped across R1, and some voltage is getting dropped across R3. Now I know since R3 is smaller than R1, then the voltage dropped across R3 would be less as well. And why is this? Well, what is the voltage dropped across R3? According to this formula, it's just I, which is the current in the circuit, times R3. And what is the voltage dropped across R1? Voltage dropped across R1 is the same I, but times R1. So the voltage dropped across R1 is greater, or voltage dropped across R3 is greater? Well, I times R3 would be definitely less than I times R1 because R3 is less than R1. So what I'm trying to say with all that is that the voltage dropped across R3 would be less. So that means most of the 5 volts will get dropped across R1, and less of the 5 volt would get dropped across R3. And so I know 1.66 is dropped across R3, so 3 point some volts will be dropped across R1, and that's how I intuitively know that everything's looking good, everything's correct. And let's go ahead and simulate. So I'm going to hit run and perform a stop time transient analysis of 1 second. And now let's see. Okay, so I hover over R1 to see the current, but you can see the direction of the current that's shown with the red arrow is this way, going this way. But we know that the voltage source is here and the current should be flowing this way. But you don't need to worry here. It's just that the simulation tool is assuming a direction for the current, and it's assumed the direction of the current to be from this node to this node. So essentially our voltage or our current value should be negative because actually the current is flowing from here to here, right? So if we click on here, now we can see the value is 33.33 milliamps like we calculated before, and we have a negative sign. That's what we expected. The second thing we want to know is what is the voltage at this node? So let's click here and we see V node 2 in blue. You can see that this is 1.66 volts like we calculated. So hopefully you were able to follow along, and we learned things like the voltage divider here. We learned how to combine parallel series resistances. We learned intuitive understandings of when we're calculating the voltage drop across resistances, which one would drop more, which one would drop less, and yeah, how to calculate the voltage across or between these two resistances, series resistances. And we also did a transient analysis on simulation. There we go. So yeah, if you have any questions, please reach out to me. I'd be happy to answer that for you to get more and more clarity on this subject.